Good morning. It's time to start a new chapter. This time we're starting the structure of atoms and their electron configurations is what we're going to be looking at. How are those electrons put together? This is going to be a real important key to chemistry. We're going to find out that those electrons and how they are arranged inside of an atom influences most all of the properties that an element has. It determines whether an element is shiny, how it's going to react with other things. It's going to determine pretty much, like I said, almost everything about it. So this is a really important piece of chemistry to understand. So it'll also explain a lot of things later on as we progress through chemistry, or if you continue on with chemistry later on. So your notes should look. You should have already copied them down. It should be the notes like this, where it starts with the atom at the top. So that's what we're going to be going over. All right. So what's the atom? I'm hoping you've already heard about the atom before, but it is that smallest particle of an element that retains all the properties of the element. We talked about way back when my ring, it's made out of titanium. If I could take, which my ring is kind of silver in color, it's really, really hard. It's a very heavy metal. If I take one atom out of there, if I could actually do that, then it would look exactly the same. It would be kind of that silverish color. It'd be really, really hard. It would be a very heavy atom. Right, it would have exactly all of the same properties, and that is as small as I can get, and still have all those same properties. Right. If I go less than that, which is what we're going to look at in this chapter, then it doesn't have those. So this atom is as small as we can go. Now, many years ago, in the 1800s, well, let me rephrase that. Early 1900s, there was a gentleman last name of Dalton that developed an atomic theory. And he came up with four things that he believed were true about all matter. And what we're going to do is we're going to go through this and look at it. And I will tell you that, chemists actually look at it and say, yeah, they are true. Right? However, there are some things that we have now currently found that we can do that don't exactly follow Dalton's theory. However, we still accept Dalton's atomic theory as true because it is true under normal circumstances. Okay? So the first one, all elements composed of tiny, indivisible particles called atoms. All right, so now what does that mean? Well, one thing is it means that we got these little atoms that we can't take them apart. Once that's as small as we can go, and we can't take them and break them down any further. Right? There's the problem. We have done that. We have taken atoms, we have torn them apart. You don't want to be around when that happens, right? The people in Nagasaki and Hiroshima, they were nearby when one of those atoms was taken apart, and that was the atomic bomb, right? And those people are no longer with us. So to divide an atom releases ungodly amounts of energy, right? So it's not something that we really want to do, but we do know, yes, we can do it. So now, again, scientists, chemists do believe that Dalton's theory is correct because atoms don't normally break down. Right? My ring sitting here right now, I'm not going to have my ring, all of a sudden the atoms are going to fall apart. That's not going to happen. Right? So we do consider them to be indivisible, really, really tiny little particles. These particles are actually so small, too, I will tell you, nobody has ever seen them. Now, you might say with that one, go, well, if we ain't ever seen it, then why in the world are you teaching it, Mr. Pay? How do you know? Well, I will tell you, scientists have done experiments upon experiments upon experiments. They keep doing experiments, and every time they do one, they keep coming up with that all of this stuff is true, right? It's going to be a really, really hard thing to disprove this if it ever were to happen. Because it just keeps getting, every experiment we do keeps coming up with that. This is the way in which atoms are put together, right? How they are arranged and what they do. So that's why we accept it, right? And we accept it because the experts, the people that have studied this their entire life, this is what they have found. So we accept that as true because that's what they've done. All right, second part to Dalton's atomic theory is atoms of the same element are identical. That first piece, that means this atom on this side of my ring and this atom on this side of my ring are exactly the same because it's the element titanium, right? So all titanium elements look exactly the same. The second part to that, atoms of each element are different from atoms of all other elements. If I had my other gold ring from way back when and I took an atom out of that atom's going to look different than the atoms in this ring because they're gold versus titanium. So atoms of different elements do look different. And again, in this chapter, we'll get an understanding of what those atoms look like, and you'll be able to tell me what they look like and how they are different from each other. Okay. And that one to say that all elements are the same, as we go through this chapter, we are going to find out that there are ways in which the atoms of this ring, how they can be different. Okay? And again, that will be something we'll talk about later when we talk about ions, and we're going to talk about isotopes, which will make sense later to find out. But again, scientists look at this and say, in normal conditions, it's true. All these atoms are exactly the same that are inside my ring. Right? All right, third thing, atoms combine to form compounds. So atoms go together and make compounds, which we talked about in the last chapter when we had water, and water was H2O. So we have two elements that go together. We got hydrogen and oxygen. They combine together, and it makes water. Right? And then we also got sodium chloride. And that's two elements that go together, and once they go together, they make a compound. So that one there is no controversy over because elements do go together to form compounds. The last part, number 4, chemical reactions occur when atoms are separated, joined, or rearranged. That part is true. All right, so we either rearrange them, we separate them, so we can take this water. If I run electricity through water, real high electricity, then I can get the water to the elements that are in there to pull apart. I can get oxygen to come off, and I can get hydrogen to come off. Right? Different than the idea of boiling it. When I boil it, then I get water as a unit come off. Right? But we can actually, under special circumstances, we can take these elements and pull them apart in a compound. Atoms are not changed into new atoms of other elements. So that's saying that we can't take any of these elements that are up here. We cannot change them into any kind of new elements. And that is true. However, we have currently, within the last, about 40 years, we have been able to make new elements. And that's actually what's on the bottom part of the periodic table. If you were to go to your periodic table, when we look at these elements right here, the ones that are in white on this one, those are elements that scientists have artificially made. Right? The last one that they made was this guy way over here, element 118. He was around for 1/20,000th of a second. So that's not even a second, right? Not even really hardly a part of a second. That's like take 1 second divided into 20,000 pieces and one of those. So it was like, here, gone. That was it. How did scientists be able to see that? I don't know. I'm not a nuclear physicist. That's how they do that. But I understand that that's what they have done. Now, how did they put them together? The way in which I like to describe it is they take an atom of a really, really heavy element, and heavy elements are the ones that are down here in the bottom of the periodic table, and they strap it to a wall. And then they take another element, or basically protons, and they run them through a tube, and they get them going really, 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 really fast. They'll get them going on basically the speed of light. And then what they want to do is they want to hit that other atom. So they send them right at that other atom. The other atom's going, ah! And boom, if it hits it just right, they'll boom, go together, and it makes a new element, a new atom, but then it goes, falls apart. Right? And the scientists are able to look at it and be able to see what those properties are of that new element. Now, we don't do this very much or very often, right? And we have found that it is really hard to make them, but we do have some, again, that are on the periodic table that are synthetic is what they're called, meaning that man-made that we have produced. But again, they don't stick around for very long. But it helps us understand the atoms that are up here at the top that are naturally occurring elements that we find around the surface and the crust of the earth, right? So those are the 4 pieces to Dalton's atomic theory, right? Now I go to the next part. Number 3, there was a table that you were supposed to write down. It said atoms are made up of. And we had the particle, the symbol, the electrical charge, approximate mass, and where they are located. Right. So the first one is the proton. And the proton symbol is a P+, a little p with a little plus next to it. And that little plus means that its electrical charge, it is a positive 1. So every proton has a positive 1 charge. Now, what's its mass? The piece that I want you to know for its mass, I'm going to write it up here, is 1 AMU. Okay. That AMU stands for atomic mass unit. Because actually what they found is they found that the mass of one proton is the number that's in the parentheses in your notes, which was, actually let me, I'll write this out. It's actually this number. Is that number in grams. Okay, so this is a really, 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 really small number. All right. Now, what scientists said is, well, we can't be writing these many zeros all the time, and we can't call this thing 1 gram because it's not 1 gram. So what they decided to do is they decided to call that number 1, and then they gave it atomic mass unit, or AMU, and that's what AMU stands for, is an atomic mass unit. All right, now where do we find protons at? If I were to draw an atom, we find protons in the nucleus. They're in the center of that atom. All right. Okay, so we go on to the second particle. It's called a neutron. And neutrons, their symbol is N with a little 0 next to it. They are neutral. They have no charge. A common mistake a lot of people do is they think neutrons are negative because it starts with an N, but nope. If you look at the word neutron, it's almost got the word neutral in it, and neutral means no charge. What's its approximate mass? You should have down 1 AMU. The mass of a neutron is this number, so they made it 1 AMU. And where do we find them at? In the nucleus. They're inside the nucleus also with the protons. So basically we got protons and neutrons are almost exactly the same, except protons are positive, neutrons are neutral. Right? Everything else about them is the same. All right, then we get to the third one, the electron. The electron symbol is E negative because its charge is a -1. Now, what's its mass? We consider it to be 0 AMUs. Now, why is it 0 AMUs? Because its number is actually this, and I'll put them in line with this. It is that number. All right, so I'm trying to put it in the same lines. If you notice, this one is like here. If I were to get rid of all these zeros and make this thing into something bigger, and I pull these things down, so I'd put a 0 here and a 0, 0, 0. This one is 1, 6, 7, 0, comma 0, 0, 0. The bottom one is this. So if we make a comparison in those two, this bottom one's basically like 1,000. The top one is basically 1,000,000 in regards to protons and neutrons. So what scientists found out is, you know what, that electron is like 1,000 times less than a proton or a neutron. So scientists say, you know what, that's really nothing when we compare it. So we're going to call it 0 AMUs. So the answer for what's the mass of an electron, it is 0 AMUs. Right? I'm going to stop there for part number 1. We're going to come back for a really, really short part number 2, but I'm running out of time right now. So we will come back in a second. See you.